Tsunamis are part of Australia's history. Even though the continent is largely protected from them due to its location, with it lying in the middle of a stable tectonic plate, there is still evidence of large tsunamis hitting the mainland. The generation of tsunamis isn't only limited to large earthquakes. Submarine landslides and asteroid impacts that land in the open ocean can generate massive tsunamis that can be tall enough to ride over significant cliff faces and surge multiple kilometers inland. As you will soon see, the wave we will discuss in today's video reached heights of at least 130 meters or 426.5 feet. In today's video, we're turning to the eastern parts of Australia. Tsunami evidence exists in both New South Wales and Queensland, but we'll be focusing on the wave damage in New South Wales in this episode. I'll be drawing much of my information from a paper that was released in 2001 under the title Geological Indicators of Large Tsunami in Australia. The link to this peer-reviewed paper will be in the description. We'll be starting our journey in Jervis Bay, which is nestled along the southeastern coast of New South Wales in Australia. The Mega Tsunami waves at Jervis Bay were capable of travelling up to 10 kilometres inland, reaching elevations of more than 80 metres above sea level. The extensive inland penetration, combined with the deposition of large boulders and the formation of Chevron dunes, underscores the immense power of these ancient waves. Their study details the geological signatures left behind by these monumental waves, offering a glimpse into the ancient forces that shaped Jervis Bay. One of the most compelling pieces of evidence of these megatsunamis is found in the massive boulders strewn across the landscape. At Gumgetters Inlet, for example, Dr. Bryant discovered sandstone slabs measuring up to 7 meters in diameter, deposited at an elevation of 25 meters above the sea level. These boulders, many exceeding 2 meters in intermediate diameter, are not the result of ordinary storm waves. Their imbricated or stacked arrangement suggests they were carried and deposited by powerful forces of tsunami waves. The velocity required to transport such massive boulders is staggering, estimated to range from 7.8 to 10.3 meters per second. These findings underscore the immense energy unleashed by the tsunamis, capable of lifting and suspending huge boulders and depositing them high above the current sea level. Such boulder deposits provide a stark insight into the destructive power of these ancient waves. At Steamers Beach, located on the southern headland of Jervis Bay, lies another intriguing feature: Chevron dunes. These parabolic dunes, consisting of sand mixed with cobbles, rise from the beach to a height of 30 meters. A second deposit of sand, fine shell hash, muddy lenses and quartz pebbles forms parabolic dunes up to 130 meters or 427 feet high behind the beach. These formations, known as chevrons, a word many of you are familiar with if you watched the Burkle impact documentary that we made, are created by the run-up of sediment-laden tsunami waves, leaving behind distinct V-shaped ridges pointing inland. Despite their prominence in geological surveys, these chevrons are not easily visible on standard satellite imagery or maps. They've been heavily obscured by vegetation, making them less distinct from the air. However, their presence is unmistakable to trained geologists, who recognise these formations as clear indicators of past tsunami activity. The height of these chevrons indicates that the waves responsible for their formation were at least 130 meters, if not higher. Beyond the deposits, the erosional signatures left by these megatsunamis are equally telling. Large-scale features such as linear canyon formations, pool and cascade features, and raised ramps on headlands reveal the sculpting power of the waves. For instance, at Jervis Bay, the breaking of tsunami waves left behind inverted toothbrush-like structures, with raised ramps separated from the shoreline by eroded depressions. As a side note, if you're enjoying this video, please click the like button to help YouTube recommend it to others. Consider subscribing and clicking the bell icon to be notified of when we upload. We also have a Patreon if you'd like to support the channel, only if you have the means of course, and you can find that both in the description and in the pinned comment down below. Smaller features such as Muschelbruch, Sichulwanen, Quevedos, and flutes further illustrate the high velocity flows that carve the bedrock, akin to the erosional features seen in subglacial environments or megaflood regions. Muschelbruch, Sichulwanen and Quevedos are specific types of erosional features formed by high-velocity flows, such as those associated with tsunamis. These terms are used to describe distinct bedrock sculpturing patterns resulting from the intense energy and dynamics of such events. Muschelbruch is a German term meaning shall break, and it refers to the scallop-shaped depressions or grooves carved into the bedrock. These features are created by the turbulent flow of water, which erodes the rock surface in a pattern resembling the concave shape of a shell. They are typically formed by processes involving cavitation and abrasion. Sichelwahnen, another German term, translates to sickle troughs. These are crescent-shaped depressions or troughs carved into the bedrock by the erosive action of fast-moving water. These features form when water flows over bedrock with sufficient force to create curved, sickle-like troughs. Unfortunately, very little pictures available for me to use exist to demonstrate these phenomena. The shape results from the consistent direction and velocity of the flow. Cavettos are small concave depressions or grooves found on bedrock surfaces, often created by the erosive action of swirling water or cavitation. Cavettos form when water carrying sediments and debris flows over rock surfaces with high velocity. The swirling motion of the water creates small rounded indentations in the rock. Understanding what triggered these ancient megatsunamis is crucial. The study by Dr. Bryant and Dr. Knott points to two primary causes: large submarine landslides on the continental slope and meteorite impacts in the adjacent ocean. These forces are capable of generating the enormous energy required to produce waves of such magnitude. Submarine landslides, often triggered by seismic activity, can displace vast amounts of water, creating massive waves. Meanwhile, the impact of a meteorite crashing into the ocean or even exploding above it can produce tsunami waves with run-up heights between 10 and 100 or more meters. Aboriginal stories recounting meteorite impacts adds a cultural dimension to this geological narrative, suggesting that these cataclysmic events have left a lasting imprint on both the land and its people. Radiocarbon dating and other methods have provided a timeline for these catastrophic events. Evidence indicates that at least two significant megatsunamis occurred during the last 1,000 years. The most recent event, estimated to have occurred around 350 to 400 years ago, left behind deposits and erosional features that match those found in other regions of Australia. This event is believed to have had a substantial impact on the coastline, with waves overtopping cliffs up to 80 metres high and sweeping boulders inland. Another major event, dated to around 750 to 1050 years ago, similarly left its mark, with boulders and chevrons indicating the immense power of these waves. These timelines suggest a recurring pattern of large-scale tsunamis, possibly linked to regional seismic activity or periodic meteorite impacts. The evidence of megatsunamis at Jervis Bay is not merely of academic interest, it highlights the ongoing risks posed by such events to coastal communities. While the historic record of the last 2 centuries shows no comparable events, the geological record indicates that Australia is not immune to the devastating effects of tsunamis. Understanding the past is crucial for preparing for potential future events. The geological evidence of megatsunamis is complemented by the rich tapestry of Aboriginal oral traditions. Indigenous communities along the southeastern coast of Australia have long told stories of great waves and the forces of nature that shape their world. These narratives, passed down through generations, offer valuable insights into the historical occurrence of tsunamis and their impact on human societies. One such story speaks of a time when the sea rose up in anger, flooding the land and carrying away everything in its path. The elders described waves as tall as the highest trees, sweeping inland and reshaping the landscape. These accounts, while often dismissed as myth, align closely with the geological evidence uncovered by modern science. The integration of Aboriginal stories with geological findings creates a more holistic understanding of the history of megatsunamis. It acknowledges the deep connection between the land and its people, recognising that cultural memory can serve as a vital repository of historical knowledge. This interdisciplinary approach enriches our comprehension of past events and highlights the importance of preserving Indigenous narratives as part of our collective heritage. The study on Jervis Bay's megatsunami reveals that the direction of the tsunami waves was primarily from the southeast. This conclusion is based on several geological indicators observed in the region. The boulders found along the cliff tops and within the bay are imbricated in a manner that indicates a southeast source. This stacking pattern aligns with the direction from which the waves approached, showing that the force of water was coming from the southeast. The chevrons at Steamers Beach, which rise to 130 metres or 427 feet in height, are orientated in a way that also points to a southeast origin. These V-shaped ridges indicate the flow direction of the sediment-laden waves, confirming the southeast approach of the tsunami. We will now look at any additional evidence that exists. Remember, we are looking for a wave that hit from the southeast. One thing seems clear to me, and that is the fact that unlike the Burkle impact event and subsequent megatsunami, this wave appears to be localized rather than massively widespread. Whether a small impact occurred just off the coastline here or a submarine landslide took place is debatable, but the evidence of this event isn't quite as widespread as the Burkle Chevron deposits. But that could be because of the dense vegetation that exists here. This level of vegetation doesn't exist in the parts of Australia covered during the Burkle impact, but the wave was much taller than the 130 odd metres approximated in this event. There are a few things that stand out though. The first is this line of vegetative regrowth that has occurred in 5 Mile Beach. You can see a clear outline of where the tsunami appears to have hit at its most powerful level. A little south of here, you can see wave damage and chevron depositions at Cudmore Beach. The next point that they appear at is further south at Inyata Beach. And they appear again at Conjola Beach. After this, as we travel further south, we have multiple townships that have developed which may have erased any trace of the tsunami impact. The last spot that pokes out to me is at Wairo Beach. But there's one last thing that really stood out to me, and that's the fluted features that appear in the cliff sides further south, beginning at Emily Miller Beach and extending all the way down until North Head Beach. Just look at these features on Google Satellite. They are carved in a manner that suggests the wave hit from the southeast. I'll put a few of these locations up on the screen now. So I hope you enjoyed this look into a mega tsunami that struck New South Wales. In the coming days, I'll release a video on the wave damage and tsunami deposition in Queensland that this paper that we are covering discusses. So until then, thanks for watching. The east coast of Australia was undoubtedly hit numerous times in history by tsunamis of varying heights. In this video, we're going to continue our journey up past Sydney, beginning in Newcastle. The peer-reviewed study, Geological Indicators of Large Tsunami in Australia, released in 2001, documents the fact that tsunami deposits exist in a 400-kilometre stretch of coastline in New South Wales. I'll put the link to this paper in the description. Whilst I can't show the map included in the study due to copyright reasons, the paper details that tsunami deposits exist from north of Sydney down to Jervis Bay and stretch all the way down to Tura Point. This tsunami has also hit Lord Howe Island, and I'll make a separate video on this. The prevailing wind direction from Sydney down to Tura Point goes from a west direction to a southwesterly direction. As you will see in this video, this goes against the chevron directions that we will look at, which are deposited in a manner that points to the northwest. In the last video, it became clear that the tsunami that we covered came from the southeast and smashed the area of Jervis Bay from that direction. It deposited parabolic dune chevrons up to 130 metres high. These features are not Aeolian dunes because they contain numerous pebbles and gravel along with massive boulders of impressive size that were deposited high up over 80 metres beyond the cliff faces. It's likely that the tsunami grew in height as it became funneled into the bay, which increases the run-up height of tsunamis. This video will serve two purposes. First, we'll look at a few different areas that stick out to me. Following this, we'll look into the processes that form tsunamigenic deposits, and then we'll explore the difference between these deposits and those formed from natural processes like wind, wave, and storm action. One thing to point out is that as we head further north, the directional nature of chevrons will slowly turn from being northwest facing to just under north facing, before they no longer hit Australia. We will scour the coastline of Newcastle up to a point called Seals Rock. It's worth noting that we are attempting to follow the tsunami that struck Jervis Bay, which came from a southeast direction and occurred within the past 1,050 years. But I will also show you some formations that look like they were deposited from a different, possibly older tsunami. One last thing to note is that I'm only showing you what may be tsunami-based damage. Field study is needed to grant them the label and to reach a conclusive finding. But there are some telling signs that I will outline for you in this video. But first, what about Sydney? Well, the study details that Sydney was also the site of tsunami impacts, but much of the city has hidden any trace of tsunamigenic damage. There is one possible site that might hint to a tsunami at Endeavour Heights Reserve. If we look at the geological maps, we have scoured bedrock existing here. These bedrock mantling dune facies were seen in Jervis Bay. The cliff faces here are only 30 metres or so high, and we have parabolic dune chevrons that rise to a maximum height of 50 metres in certain parts. The dunes themselves are a mix of marine and terrestrial sediments. Tsunamis can deposit a mix of marine and terrestrial sediments, but these deposits are typically associated with tsunami run-up zones rather than aeolian processes. Tsunami deposits are characterised by a chaotic mix of materials, including marine shells, sand, gravel, and terrestrial debris, and are usually found in low-lying coastal areas affected by the wave's impact. There are fluted features seen on the bedrock here, and there's also less dense and scattered vegetations and pool features which may hint to tsunami damage. After this, the New South Wales Golf Course has removed any trace of possible chevrons, but the geological map also lists the area as being bedrock mantling dune facies. But let's head north now to the Newcastle area. Stockton Beach features something extraordinary. We have these massive chevron-shaped dunes here, but what's more telling is the fact that the dune facies extend 10 kilometres inland on geological maps. This is very telling. Another thing that's interesting is a mix of marine and terrestrial sediments are listed as occurring in these dunes. It could be inferred that the deposits have a possible tsunamigenic origin. One would need to dig through them to properly classify them as tsunamigenic, but their stretch of 10 kilometres inland is a telling sign that they may be related to a tsunami. The Tamago sandbeds reach a maximum height of 30 metres. We have another smaller dune chevron deposition at Samurai Beach. After this, we have another interesting feature. Notice these sand dunes here don't stretch all the way from the beginning of this beach. There is a possibility that we are witnessing what is known as the shadow effect here, where an area is spared from the brunt of the wave by landmasses that were in the direct line of the impact by the wave. The Yakaba headlands rises to 170 metres. As you can see, there are no sand dunes in a line where the Yakaba headlands shelter the region, only for them to briefly appear, then disappear again, as a result of Cabbage Tree Island being in the way. Fluted features are seen on the bedrock here on the southeastern side of the island, and Boondalba Island has similar features. Little Island is nothing but bedrock. If we take a moment to consider the locations of these three islands and the Yakaba headlands, a very interesting thing appears. The sand dunes diminish in size in the areas where the wave hit from the southeast, only to become most apparent when there was nothing in the wave's line of direct impact. Beach deposits exist here that stretch about 8 kilometres inland. When taking all of this into account, this is an area of very peculiar interest, and it would be worth digging the dunes themselves to see if they contain tsunamigenic deposits, which to this point hasn't happened. What has happened, however, is smaller geological sampling of the areas that stretch 8 kilometres inland. They contain fine to coarse-grained sand, seashell fragments, and gravel. These are the things one would expect to see in tsunami deposits, as wind-formed deposits don't contain gravel. The type of gravel seen here is known as polymictic gravel. Polymictic gravel is a type of gravel that is composed of a mixture of clasts or fragments of different rock types. The term polymictic comes from Greek roots meaning many mixtures, indicating the diverse origin of the gravel components. Now, to be fair, rivers carry polymictic gravel, but seeing beach ridge deposits this far inland is a sign that some high energy event swept these deposits inland. And of course, tsunamis can carry polymictic gravel. The high energy and force of a tsunami can erode, transport, and deposit a wide variety of sediments, including gravel of different rock types. I wouldn't be too surprised if beach ridge deposits were found near to the beach, but to find it 8 kilometres inland is very strange in my eyes. After this, we have another example of the shadow effect due to Broughton and Little Broughton Island, before 30-metre high sand dunes suddenly appear again. I do not believe this is a coincidence. This is the second time we have seen this. But before we continue, we need to look at something very interesting. Beach deposits extend almost 20 kilometres inland from this point, and they contain the same mix as before. Fine to coarse-grained sand, shell fragments, and polymictic gravel. It's right along the river, so the gravel could be from there, but it doesn't explain the seashells. If these are tsunamigenic in their origin, which appears highly likely due to how far inland they stretch, the reason for their impressive surge inland is due to the lake that exists here, which is the lowest point, allowing the wave to surge inland and over the lake, up through the river systems that exists here. We have now reached the area where I believe this tsunami ends, at Seal Rocks. It's worth noting the direction of the sand dunes. They are increasingly facing north as we moved up the New South Wales coastline. I want to quickly show you areas that were spared from the tsunami. These areas do not contain the same geological features that we saw in the other areas. They lack any inland penetration of sand dunes. Notice how different the coastline looks. Now I'm going to show you areas that I believe were deposited by an unrelated tsunami that I suspect was much older. At this area, I firstly laughed at the name as my inner child came out, but I also became interested in the beach ridge deposits that are 7 to 8 kilometers inland. The coastline bears no mark of any tsunami-based damage, leading me to suspect it could be a much older tsunami that deposited these seashell and gravel-rich sand dunes. Again, look at how different the rest of the coastlines here are. They do not look disturbed. This is the typical appearance they take when no possible tsunami-based damage has occurred. So before we go into the details regarding the signatures that tsunami waves can create, I want to point your attention to Hat Head. This beach has chevrons that now face a western direction, leading me to suspect another tsunami has occurred here from a different origin than the one that hit Jervis Bay. Shell material has been deposited about 8 kilometers inland here, and the next bay looks similarly disturbed. Now we'll look at one site that I believe is worth mentioning. Further north at Iluru Group camping spot, we have these features. A possible tsunami of up to 80 meters in height might have occurred here. Vegetative regrowth has grown on what appears to be ancient chevrons. A cross-section reveals these parabolic dunes vary from 58 to 78 meters high. The land here drastically rises to 130 meters, which might have served to block any further inland penetration. Now let's look into more detail at how tsunami waves can create 4 general categories of depositional and erosional signatures that distinguish them from storm waves. To start, we can use these depositional signatures to distinguish imbricated boulders deposited within coarse-grained sediment and geomorphic forms, which are much closer to the surface. Moreover, most of the identifiable sedimentary deposits are not very conspicuous in the landscape, and cannot be detected without fieldwork or more detailed studies. If an imbricated boulder train is not exposed at the Earth's surface, it won't trigger the same sense of wonder and the associated puzzle about how it got there. Both the sand laminae and the sand layers with boulders are buried below the surface. Depending on the depth a sedimentary tsunami deposit is buried, it might not be conspicuous in the landscape either. Without detailed study, they might be interpreted as a product of some other, more familiar geomorphic process. Consider the sand laminae. In the scientific literature, those deposited by a tsunami are often described as an impression structure. But although these thin-bedded, unstratified sand layers can form during severe storms or the processes of storm overwash, wave ripple, or density currents, thick sand laminae of more than 30 centimeters in thickness are most commonly associated with tsunamis. Sand laminae or lenses can be very thin and hard to detect. In fact, some of these sedimentary layering structures amount to just a few millimeters to a few centimeters of sand. Typical sand laminae are layered following the orientation of the waves that deposited the lithified sediments. These layers demonstrate a distinct grain size contrast with overlying sediment ranging from clay to coarse-grained sand. What this means is that many of the sand layers that are listed on geological maps as being wind-formed are done so by eye, rather than by examination. This is an issue because it omits any potential tsunamigenic evidence. The sand dunes themselves need to be dug and investigated to prove a tsunami origin, and this is something that has scarcely been done. This is why the directional features that are present on maps are important. They go against the direction of prevailing winds, and instead they're deposited in line with a tsunami that originated from a southeastern direction. If these are wind-formed, they should either point to the west or to the southwest, but they don't. They point to the northwest. Chaotic sediment mixtures or dump deposits can also be challenging to interpret. These deposits can form from various processes, including solifluction, ice push, human disturbance, or slope wash. Solifluction is the slow downhill flow of water-saturated soil over a frozen or impermeable layer, typically occurring in cold climates with permafrost or seasonal frost. However, in coastal areas without ice, ground freezing, or human disturbance, such deposits can be attributed to catastrophic tsunamis capable of transporting and depositing large volumes of sediment with minimal sorting in a short period. Coarser dump deposits, often containing cobbles and boulders, are typically found plastered against the sides or on top of the headlands. These deposits might be mistaken for storm deposits, but several factors differentiate them. Storm waves tend to separate sand and boulder materials. With storms combing sand from beaches into the nearshore zone, and moving cobbles and boulders landward to form storm berms. While exceptional storms might toss sediment onto cliff tops more than 15 metres above sea level, tsunami dump deposits can be found on cliffs much higher, of between 20 to 30 metres, and in sheltered positions. Tsunamis generated by submarine landslides can deposit mixed sand and boulder material to considerable elevations. For instance, on the island of Lanai in Hawaii, such deposits have been found several hundred metres above sea level. Enigmatic deposits on headlands, labelled smear deposits, are spread in thin layers, less than 30 centimetres over the steep sides and flatter tops of the headlands, reaching elevations of 20 to 30 metres above sea level. These deposits contain 5 to 20% sand, shell and gravel, and are not products of in situ weathering, as they often contain quartz sand not found in the underlying bedrock of volcanic sandstone or basalt. These smear deposits formed a traction carpet at the base of sediment-rich flows overwashing headlands. The most dramatic tsunami deposits are large boulders piled above the level of storm waves. These boulders, up to 106 metres cubed in volume and weighing as much as 286 tonnes, are imbricated and stacked in parallel lines along the east coast of Australia. For example, at Jervis Bay, blocks weighing almost 100 tonnes have been moved in suspension above storm wave limits to cliff tops 33 metres above sea level. These boulders are orientated according to the direction of the tsunami wave approach, not at right angles to the cliff line, indicating the immense power of tsunami overwash. Hydrological calculations confirm that only tsunamis and not storm waves have the power to move such large blocks onto cliffs. These parallel imbricated boulder piles are the unmistakable signature of tsunami overwash. Except for karstland, which represents the planing or smoothing of raised estuarine surfaces by tsunami run-up, tsunami depositional forms could be misinterpreted as features built by swell or storm waves. However, their internal fabric and chronostratigraphy differ from those produced by storm waves. For example, ridges and mounds above the high tide line at Bass Point contain chaotic mixtures of boulders, gravel, sand and shell, with steep sides combed down by storm waves. These landforms, with their wide range of grain sizes, bear no resemblance to storm or swell wave deposits described in the sedimentological literature. Their closest analogue is an ice push ridge, but the New South Wales coast is unaffected by ice push processes. Chronological inconsistencies have been identified at over 8 sites along the southeast coast. One notable example is a Holocene barrier at Bellambi, 60 kilometres south of Sydney. This barrier, seemingly formed by the Holocene marine transgression within the last 6,000 years, contains sands dated to over 22,000 before present, based on thermoluminescent dating. Pumice within the deposit dates to the same age. These old sands, however, overlie estuarine sediments radiocarbon dated to 6,560 before present. The sands were originally wind-blown material deposited on the shelf when sea levels were lower during the last glacial period. Recently, they were swept from their shelf by tsunamis and deposited at the shore as a barrier feature without resetting their TL clock. Tsunamis have occurred here at approximately 6,500, 2,900, 1,500, 900, and 222 to 250 before present. The most significant events in terms of size and extent took place around 6,500 before present and 900 before present, both having a major impact on the coastal evolution over more than 400 kilometres of coastline. So the last areas that we looked at in this video might be from the tsunami of 6,500 before present, due to the vegetative regrowth that has occurred, whereas the more obvious dune chevrons could be from 900 before present. Only 3 mechanisms can generate waves large enough to create the features found around the Australian coastline: submarine landslides, meteorites crashing into or exploding over the ocean, and large submarine volcanic eruptions. While all 3 factors are possible, especially for the south coast of New South Wales, the fragmentation of a large meteorite impacting the oceans around Australia is the only mechanism that can explain the coincidence in dates. Huggett 1989 calculated that an object as small as 0.2 kilometres in diameter crashing into the ocean could produce tsunamis with run-up heights of 10 to 100 metres. Meteorites of this size have a theoretical recurrence interval for the Pacific Ocean of 24,000 to 43,000 years. Smaller objects can also generate tsunamis, but with greater frequency. Indigenous stories also describe the impact of meteorites. From a risk perspective, the occurrence of cosmogenic megatsunamis is ambiguous. However, without such a mechanism, one must conclude that megatsunamis may be a natural and regular geological induced feature of the Australian coastline. So I hope you enjoyed this detailed look into the tsunamigenic damage of Eastern Australia. We'll continue this journey in future videos. And as always, thanks for watching. Are you interested in animals? I've just started a second channel called PaleoZoology that discusses extinct and extant animals with a current focus on the megafauna that once dominated and roamed Australia. I've released a video on the Marsupial Lion which existed in Australia during the time Indigenous Australians walked the continent. I've also covered the wombat that was the size of a car, known as the Diprotodon, or the largest terrestrial lizard known as the Megalania. I'd love to have you along for the journey as more videos are released. You can find a link to this channel and to the aforementioned videos in the description and in the pinned comment in the comment section. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.